My final presentation for Underactuated Robotics is on model predictive control for vehicle path tracking in a 3D simulator. Model predictive control solves a convex optimization problem at every time step. At every sample time, it queries the car from the simulator for its current state, predicts its motion forward in time for a set time horizon, compares its trajectory with the reference trajectory, and then feeds it into the optimizer. Once we solve this optimization problem, the first output of the control signal is fed back to the car in the simulator. My Mpc problem formulation aimed to minimize the cost over input, the difference in the input between time steps, and also the difference between the car's reference trajectory and the car's predicted trajectory. My baseline for comparison is the pure pursuit algorithm I implemented in Mpc. Here you can see it operating at 8 meters per second with a drive command sent at a rate of 50 Hz. The pure pursuit algorithm calculates the curvature of the vehicle to a point on a trajectory a certain look-ahead distance away, and then sends a steering angle based on that look-ahead. So it's fast to implement. There are no concerns about computational limits because it's not solving an optimization problem like Mpc, but there are some shortcomings. As shown in the video, the algorithm cuts corners and it also requires very careful trajectory tuning. As you can see in the corners, I had to design my trajectory to purposefully overshoot the corners in order for the vehicle to not cut the corners short and collide with obstacles. Pure Pursuit can handle some drifting, but it also does not take into account the true vehicle dynamics and wheel slip because it uses the kinematic bicycle model. For my Mpc implementation in Mpc, you can see that we successfully get it to follow a trajectory that closely resembles the shape of the road. There's not as much of an undershooting or overshooting problem as in Pure Pursuit. This is fantastic. However, the computational limits of having to solve an optimization problem at every time step becomes a severe issue when trying to operate at faster speeds. In the video on the right-hand side, you can see the car operating at 6 meters per second with drive commands being sent at a rate of 13 Hz. From experience, in order for the Mpc simulator car to run any faster without oscillations, drive commands need to be sent at a rate of 15-20 Hz or even higher. Having to solve an optimization problem at every time step, which limits the rate that we can send drive commands, becomes an issue when trying to operate the car at faster speeds. As a workaround, I tried to shorten the horizon length as much as possible, and the horizon time is the number of time steps that the car tries to predict its motion into the future. The algorithm sometimes overshoots corners due to the short horizon length. However, overall, it's still able to follow the trajectory pretty accurately. You can see qualitatively the Mpc trajectory on the right-hand side is able to be designed to be much more close to the ideal trajectory on the road. And in this next slide, you can see from these plots that the Mpc algorithm is able to keep the car much closer to the corners. Its Crosstrack error is overall lower than the Pure Pursuit algorithm, both operating at 6 meters per second. When analyzing the Crosstrack error of Mpc and Pure Pursuit running at 8 meters per second, you can see that Mpc generally still has a lower crosstrack error around turns. However, along the straightaways, it starts to oscillate pretty heavily. You can see in the video that it's still able to follow the trajectory without collisions. However, the oscillations are due to the fact that drive commands are only being sent at a rate of around 11 Hz. This leads into future work. We should explore different solvers. I use CVXPy with an OSQP solver on the back end, but there could be solvers that are more suited to these online applications. We can consider nonlinear vehicle dynamics that take into account wheel slip. We can consider different Mpc problem formulations, such as taking into account race time or progress along the trajectory over the horizon. And one very important thing that we need to optimize is the design of the path in the first place. Right now, I'm using a piecewise linear trajectory. However, it causes numerical errors where the lines meet along the sharp corners, and the trajectory doesn't necessarily obey vehicle constraints. And it also is not optimized to make the vehicle go as fast as possible if it follows the trajectory exactly.